Good afternoon, everyone. Welcome to lecture 2. Some quick announcements. So homework 1 has been posted on Canvas. You can access the PDF. It's due in 2 weeks, and there is also Labor Day in between, and I will also not have the lecture next Wednesday. So basically, whatever we will cover today and Monday is mostly part of the homework. It's due in 2 weeks. We'll have office hours, and I'll have office hours. Felipe will have office hours, so we'll have plenty of opportunities to ask questions. So, and this will be submitted via Gradescope. I think all of you have joined Gradescope, but in case you have not, just let us know and we can add you. And it'll be due in 2 weeks. All right. And then, as promised last time, we have posted 2 supplementary videos. Those videos are about 10 to 15 minutes or so, and they go into a little bit more in-depth discussion of things we'll do in class, just a little bit more slowly, giving some more examples in case you want to have more clarity in some of the concepts. Okay, so the videos have been posted. There's a YouTube playlist link. Just click on that link and you will have all the lecture recordings and supplementary videos being added on that link. We'll also post all the PDFs. So whatever we write here, whatever there is in the supplementary video will also be have as a PDF if you prefer to read rather than listen to a video. Okay. Any questions on homeworks and or supplementary videos or anything like that? All good. All right. Okay. So let's begin today's lecture. So quick recap of what we discussed in last class. And so we started by talking about different kinds of transport processes. And the first thing we discussed was heat conduction. And we wrote down the Fourier's law. We said flux is a vector with a direction and a magnitude, and it's calculated by gradient of temperature. So recall this was heat flux. It had a units of joule per meter square second. We had thermal conductivity. Thermal conductivity here, K. We found the units last time. And then this was gradient of temperature, which is simply del T by del X Ex plus del T by del Y Ey plus del T by del Z Ez. Okay, so this is how, if you know the temperature profile, you can calculate a gradient of the temperature, multiply with the thermal conductivity, and you will get the heat conductive flux. Okay, so that was the first thing we discussed. Then the second thing we discussed was how to calculate flux on a surface, right? So flux through a surface. That was the second thing we discussed, that all right, we know the total flux, but what if I'm interested in finding flux through a specific surface rather than a general flux value? And that's what we defined was the Qn and dot. Okay. And there was a question last time, which I forgot to mention, that note the vectors will always be represented by bars at the bottom. But when you see an n cap, just remember that cap is a unit vector. Okay. So this is the convention we will use, that whenever you see a hat or a cap on top of a symbol, that means the vector and a unit vector. So there are two parts of that. Okay. So n cap, Qn n cap, the Qn is given by Q vector dotted with n cap. Okay. So you basically project the vector on the n and where n is the unit normal, and that's how you can find the flux Qn n cap, where n cap is the unit vector, and to calculate n cap, we discussed you can use gradient of f, the gradient of, and divide by the say, go ahead, Colin.
So Ex, Ey, and Ez, aren't they unit vectors?
They're also unit vectors, correct. So you're absolutely right. So what if my surface, for instance, let's say is parallel to, is perpendicular, the normal to the surface is Ex, for instance, right? So when I'll take a dot with the Q vector, then I'll only get del T by del X, which makes sense that, let's say, if I have 3 dimension, X, Y, and Z, right? And my surface is perpendicular to the X direction. So this is YZ plane, right? Then the only flux that will happen is Q dot Ex, right? And Q dot Ex is simply del T by del X, which makes sense because the other 2 fluxes will not conflict, right? So n cap is a unit vector, but it is a unit vector normal to the surface. Okay. So n cap, I probably didn't specify correctly. N cap is the unit vector normal to the surface. So this is the property. It is not any unit vector. It is the unit vector normal to the surface. And how do we find that? And that is how we find it is by using gradient of f by mod of gradient of f, where f is a shape function.
So we sort of mentioned last time, how do we choose plus or minus, or sort of not matter what convention?
Yeah, it doesn't matter. So just stick to the convention you choose. So let's say we choose plus, make sure you're using plus everywhere. If you're using negative, you choose negative. Okay. This is, note that this is for a heat conductive flux. This will also be true for a species conductive, species diffusion. But we will define a convention as we go later in part 2. But for fluxes, it doesn't matter. Just pick one convention and follow. It will come out to be the same. Great questions. Any other questions at this point? All right. Okay. So this is the two. These are the two things we discussed. We also did an example. So we did an example, couple of examples here, and and we tried to find these values of flux through a surface. All right. Now let's go to the second part, which we just started and did not finish, is species diffusion. So we started discussing about species diffusion, and we said that species diffusion has, we will write the flux, total flux, in two parts. One is a mass average velocity, and the other is the molar average velocity. So let's do this slowly, because I know this is one of the most tricky concepts in species diffusion. Okay. So we had just written these equations last time, that the left hand side is the total flux. So this is the total flux, units of kg per meter squared second. So this is the mass flux, and this is the molar flux. This is also a total flux, but in the units of mole per meter squared second. We said to convert from mass to mole, all you do is you divide by the molar mass. Okay, where m is the molar mass, and has units of kg per mole. Okay. Now we also define the density rho I. So rho I is the density. V is the mass average velocity. Is the mass average velocity. Okay. And Ci is the concentration. And Vm is the molar average velocity. Okay. So any questions on these definitions of V, Vm? And I'll come to some of the definitions of Ji, capital Ji in a second. Any questions on the definitions till now? Okay, all right, so let's keep going. So we also discussed that Ci can be found by dividing mass density by molar mass, which makes sense that we go from kg per meter cube to a mole per meter cube. So the Ci is mole per meter cube. Okay. And now let's discuss, remember that we discussed this definition of velocity, mass average velocity, molar average velocity. And this is the point that I think most students get confused by. And there was an excellent question towards the end of the class, which I repeat, is that what will happen to diffusion if I take the system collectively? Okay. So remember that we said there's a total flux, we'll break it down into a mean flux. So this first part here, let's highlight it with a different color. So this part, rho I V, is the mean flux, and Ji is the flux which is deviation from that mean. Okay. Now, if I take the flux of all the components, should there be any diffusion? No, right? Because there is, everything is now included, so that they will all move together collectively as a mean. So that's the definition of diffusion, that if you're thinking of individual species, there can be diffusion, but if I'm thinking of the whole system, there cannot be any diffusion. Okay. So from that perspective, now if I sum all small ni's, sum over mass fluxes, total mass fluxes, we just say sum over total mass fluxes, So then I get summation of ni, and I hope all of you are familiar with this, but if not, don't worry, let's just take a look at this once more. So what I'm saying, I'm taking a summation of this equation, okay? The ni rho I v, I'm just taking a summation of that. And note that if I take a summation, I just add a summation sign everywhere, but velocity is common. Velocity does not change. So I'll just sum over rho I and summation over ji. Okay, summation over ji. And by definition, again, but note by definition, because I'm using a mass average velocity, then my mass diffusive fluxes summation will be 0. Okay, I'll clarify this point several times today, but this will be 0 by definition. It was an excellent question last time. I think a couple of students asked this, that this is not some like something that this is by definition. This is just the way we define the diffusion. Okay, so if you do that, that means my velocity is summation of ni by rho I and sometimes is referred to as summation of ni by rho, where rho being the total density, which we have just added all the species. Okay. So does that make sense? Yeah, please go ahead.
And the distinction here is if we had, say, 1 mole or 2 moles, that this wouldn't carry through the same way that some JIs would not be.
So they will always be, regardless of the reaction or anything. As long as you're using the mass.
Yes.
Yes. So if you're using the mass fluxes and you're dividing the fluxes into a mass and flux of units, you will always use it, regardless of what you do. That's the definition. Let's say that I have defined diffusion in a way that I can never have a total diffusion. So that's the always. That's a great question, actually. I will discuss that separately about reactions in a bit. But yeah, but this will always be true. Regardless of reactions or whatever is going on in your system, this has to hold. If it doesn't hold, your system is inconsistent. It has to hold. Okay. So great segue into the question that I wanted to ask is, now think of this. We have said summation of ji is equal to 0. Now let's go and ask this first question. Hopefully the polling will work. Let me try this time. Let's see if all of you can log into this. And sometimes it does, sometimes it doesn't work. Can you see this on your? It still doesn't work. No? Okay, it should work now, hopefully. Okay. Yeah, this is what we figured, that I just had to wait longer. All right, so I have gotten one responses. Yeah, just respond. Again, these are just to record, that you're following, and there is no like positive or negative score here. Okay. So I'll give another maybe let's say 30 seconds for everyone to participate, and then I'll close the poll. So we know that small ji is true, as was just asked. Do you think that the relation capital Ji is equal to 0 will also hold true? Okay. All right, last 5 seconds. All right, I'll stop the poll now. Please do make sure you put in your response. All right, don't worry if you didn't. We'll have more options, to do that. So let's look at the results. So your half it's split, yes and no is split. So now I want you to talk to your neighbor and discuss with them. And obviously half of you have done yes and half of you have done no. So hopefully there will be some exchange of thoughts. So think about it. Why do you think you'll pick yes or no? Okay, talk to each other, and then in 30 seconds we'll start.
But these are not necessary. Yes. And so one whole city, one whole
All right, let's start with maybe any volunteer groups, anybody who changed their answer. Anybody wants to volunteer? Yes, please, go ahead.
Okay, so my reasoning was originally because I just kept mentioning it's because of the mass average velocity, so that kind of means that it's, and we were saying there's a conservation of mass. It's always true, but it's not necessarily a conservation of moles.
Mhm.
So.
Okay, good.
that's kind of-
Okay, so I'm guessing you're
So
saying
no.
the answer is no. Yeah. Right. Yeah, good. So I think you are all going into the right sort of direction. Great. So let me try to now simplify the answer. So all of you are thinking on the right direction. But these statements, the way we should think about them is not necessarily through a reaction or conservation of modes. Right? This is by definition. Okay. By definition, small gi is zero. We know that, right? Now, what is the relationship between capital Gi and small gi? So let's look at that. So what is the relationship between capital Gi and small gi? What do you think would be the relationship between capital Gi and small gi? Is that we just divide by the molar mass, right? So we get to Mi. So what we are saying is small gi is simply capital Gi times Mi. Okay. And so summation of Gi is summation of capital Gi Mi is equal to 0. This is again by definition. I have not done anything else here. I have said that simply small gi is capital Gi times Mi is equal to 0. Now, for summation of Gi to be 0, I should be able to take this molar mass Mi out of the summation, right? So if my species, all the species have the same molar mass, right? Then that Mi factor will be constant. It doesn't change from one species to another, and then you can get it out. And that's when you can have the summation of capital Gi to be 0, but it is not a statement which is true always. Okay, so it is not implying that if summation Gi is 0, then summation capital Gi Mi is 0. Okay, so it's basically summation capital Gi is 0, but instead summation capital Gi Mi is 0. That's always going to happen. Okay, so does it make sense? Any questions on this? Okay, please go ahead.
So it's all one species, then it's zero, otherwise, and then it might not be.
So if there's only one species, then diffusion itself is sort of redundant, right? Because then how will you have, if it's just one species, then it's whatever it's moving by, that's the mean. So you have to have two species to be about diffusion. So it makes sense? Great question. Any other questions here? All right, perfect. So hopefully, so you'll get used to this. So don't worry. This I realize it's not always intuitive because this is not typically how we read about diffusion. It will become more and more obvious as we go along. Okay. So now we have said by definition, capital Gi is 0. That does not necessarily imply that's summation small gi is 0. Does not necessarily imply that summation capital Gi is 0 because there is a molar mass factor. Now let's start to think about the other part, which is the molar average velocity. So now let's think about the molar average velocity. Molar average velocity. Okay. So what is the molar average velocity is we'll sum all the molar fluxes. We'll sum all molar fluxes and we'll say summation of capital Ni. So I'm just doing the same equation. I'll just write the equation here for you. CIVM plus Gi of M. Summation capital fluxes, summation VM, summation CI plus summation capital Gi of M. Okay. Now note that when I have said my molar velocity is there, then when the summation of the molar fluxes will be zero. Okay. So that now I can by definition, this would be 0. Okay, does it make sense? Because that now I'm using my moles to be a way to define a mean velocity. And you might wonder why, how can I have two different mean velocities? Because that is how I'm defining my choice. If this becomes a little confusing, that in the supplementary video, I actually go through an example and give you an example of how you can have two different mean velocities and still have a consistent definition. Okay. So if you choose molar basis to define the velocity, then your capital JIM will be 0. If you use mass as the velocity, then your small gi. Okay. So that is the difference. And this means that my molar velocity would be summation of Ni, a summation of Ci, or summation of Ni by C, which is the total concentration. Okay. Make sense? Any questions on this? Any confusion here with the definition? Okay. So remember, what you have used as your mean velocity dictates which diffusive sum will be 0. If it's the mass average velocity, then it's the mass diffusive flux will be 0. If it's the molar average velocity, it's the sum of the molar diffusive flux will be 0. So that's how you define your velocity. And I will explain why. When do you today? We will go through the cases when one of them will be used over the other. So it'll become hopefully clearer. All right. So let's carry on. So we have done this now. So we have till now defined. We have defined. So we have defined total fluxes, total convective and diffusive fluxes. Okay. What we have not done yet is how is diffusive flux related to the concentration. Okay. So how is the diffusive flux related to concentration or density, either or, concentration / density. Okay. How is the diffusive flux related to this? So this is now the question. So first we have defined the total flux. Our species can be divided into a mean flux plus a diffusive flux. We have defined the definition of a Vm, Jm, and a Vj, so on. And now we want to understand how the diffusive flux related to the concentration. So I presume some of you definitely remember undergrad. What is the law which defines that? Fixed law, right? That's the first law is how you relate the fluxes to the concentration difference. Now I will write an equation that some of you may have seen, but many of you may not have seen, because that is a true definition of fixed law. And so you will see that's slightly different than what you read. And then you will simplify it to the form that you might most likely have seen, because that's actually not always true. So let's define the most general form of fixed law. So it is only true for binary mixture. Okay, so true only for binary mixture. So let's imagine there are only two components, A and B. All right. So first, that's the first part. It is only true for binary mixture A and B. And what we will say is JA. So note this is very important. JA is minus rho BAB gradient of omega A or WA, where omega A is the mass fraction, is equal to rho A by rho, total density. And JB is minus rho dBA gradient of omega B, where omega B is rho B by rho A plus rho B, to rho B by rho. Okay. So just quick show of hands, how many of you have seen this definition of fixed law? Few of you have seen it. Good. So most of you may not have seen it, and that's completely fine. So note that fixed law does not say that concentration gradient drives the flux. It says mass fraction drives the flux. Okay? That's the correct way to think about it, is that omega A is actually the ratio of densities, right? So if you have a gradient in densities, a gradient in mass fraction, That's what drives the most. That's a flux. And note one thing here on the left hand side, I have a JA without any superscript. That's why I'm using a gradient in the mass fraction. Now remember that capital JA would simply be small ja by ma, right? This is what we discussed earlier. So you get this as your molar flux. And JB would be JB by MB. This would be minus rho dBA MB by grad omega B. Okay. So this is your mass flux and the molar flux. So why am I using a gradient in mass fraction? Because I don't have a superscript and these are defined based on a mass average velocity. Okay. If I define something on a mass average velocity, the gradients need to be mass fraction. Okay. What do I mean by that? Now let's say I want to push this and think about molar fluxes, molar average velocity. Then I will have JA of capital M, and that will be defined by minus CDAB, gradient of chi A, where chi is the molar fraction. Again, very super important to understand this and be conceptually clear about what is the definition of DBA, CDBA, gradient of chi B, where chi B is CB plus CA plus CB, CB plus C. Okay, I hope that makes sense. I'm using a gradient in mole fraction here because these are the fluxes defined on the molar average velocity. If my fluxes are defined on the mass average velocity, I use a gradient in mass fractions. Okay. The confusion happens because we use also the change from mass diffusive fluxes to molar diffusive fluxes. But the basis is always the mass average velocity. Okay. For the top four formulas of small j, small jb, small capital J, capital JB, the basis is always mass average velocity, right? So you have to use the gradient in mass fractions. But as soon as I change my basis, my gradient becomes the molar fraction. So that's the idea. Now there is a factor that I've used here, dBA and dAB, and these are called diffusivities. Okay, so this is the diffusivity of A in B, and this is the diffusivity of B in A. Diffusivity of B in A. All right. So my question now to and just this is just a quick side note. We'll discuss this in a bit, but the units of DAB you can find out, or dBA, are meter square per second. Okay, it's pretty simple to find out the units. Just note that units are meter square per second, because you know the units of J, kg per meter square second, density is kg per meter cube, gradient has units of meter inverse. So if you multiply, you get meter square per second. Now, how I want to relate DAB and dBA. Okay, that's now I want to understand, because I don't want to carry around two different diffusivities. What can I do? How should I try to simplify? Does everybody see what was suggested? That we know by definition small ja, small ji sum is 0, right? So ja plus jb has to be 0, right? Because there are only two species. So by definition, small ja plus small jb is equal to 0, which will imply, if you sum them, minus rho dab grad gamma a minus rho dba grad gamma b is equal to 0. And we know that gamma a plus gamma b is equal to 1. So grad gamma a plus grad gamma b, I'm now differentiating, would be 0, or grad gamma a is equal to minus grad gamma b. And if you substitute this back here, you'll find that dab is equal to BB. So I know I've done it a little bit fast, but it's not that difficult. You can always do it a little bit at home if you want. But essentially, you can convince yourself to substitute that these two diffusivity are equal, that diffusivity of A in B and diffusivity of B in A are equal. Okay. Any questions at this point? Yes, please. Yeah, so that's a great question. So because we only have two components, right? Omega A and B. The omega A is rho A plus by rho and omega B is rho B by rho. So if you add them, you get rho A plus rho B by rho, which is rho by rho. Any other questions? Please feel free to ask anything, anything is confusing or formulas are confusing and so on. Okay. So till now we have said, okay, first things, we define total fluxes, we divide it into mean flux, diffusive flux. We had mean flux from two different definitions, either the mass average velocity or the molar average velocity. Now we have gone further, we have said when we use the mass average velocity, we use mass fractions as a way to drive the flux. And when we have the molar average velocity, we use the molar fractions to that. Okay, so that is what we have discussed till now. So let's take another question, and hopefully this will further emphasize the difference. Is that, do you think this is true? Do you think JA is equal to JM? And let's do a quick poll here. Hopefully it will come in a few seconds. All of you would be able to see in your screens. Let's wait. Once it turns red, hopefully you will be able to see it's not red yet. Yes, hopefully now you can see. All right, so let's take a 45 seconds to think about this. Are they equal? Is it the same? Yes, no. Take a look and think about it. I'll give another maybe 30 seconds. All right, I'll end the poll now, and then let's look at the results. Okay, so most of you have the idea correct. If the answer is no, and let's discuss how. And even if you answered it, it is confusing. I realize that, and I always myself get confused many times on this. So let's try to understand why JA is not equal to JA of M, and let's do this now. So by definition of JA, we just wrote this is actually equal to minus rho DAB by MA gradient of omega A. Okay, so don't forget that even though it's a molar flux, it's defined on a mass average velocity. So this is my definition of JA, whereas my JA of M is actually minus C DAB gradient of chi A. So my C gradient of chi A. And so these are two different definitions. They are not going to be equal. In your homework problem, in your homework 1 problem second, you'll actually find conditions when they will be equal. You'll see that's very specific scenarios that they actually come out to be the same. Okay, so they are not going to be same because you can see that one is based on mass fraction, one is based on mole fraction. So even though the left hand side is both molar fluxes, the basis of diffusive fluxes is different, so they don't have necessarily the same value. Okay, so this is what the two definitions are. All right. So with that in mind, now the next question is: should we always be using this formula? Should we go towards mass fraction, mole fraction, and so on? And this is also only true for two components, right? One, and it's a binary system. In reality, you may not have just a binary system, you may have several components. So what are the simplifications we can do? So let's discuss some simplifications. So simplifications, and this is very important to understand. Okay, simplifications. First is constant rho. Okay, so binary system, but constant density. All right. So what do you think if I have a constant total density? What should I use as my basis? Should I use mass average velocity or should I use molar average velocity? Mass average velocity, right? Because my mass average velocity has a rho in the denominator here, right? A rho in the denominator here, so it's just constant. This makes my life easy. So I should use the mass average velocity, in which case my JA, because this is a binary system, becomes minus rho DAB by MA grad of, remember it is rho A by rho, okay? Because rho is constant, I can just cancel this, right? Rho is constant, it can go out from the gradient, gets cancelled with this factor, and this becomes minus DAB gradient of rho A by MA. I just taken MA inside to keep it simple and show this becomes gradient of CA. Okay, and I believe many of you would have seen this definition that the flux is actually diffusivity times gradient of the concentration. Okay? But this is not always true. Note that we can use this when you have constant rho. Okay? So when are rho's constant? Sorry? Incompressible. In liquids, right? In liquids, typically you can expect the densities will not change, right? But if you have a gas phase system, if some of you are going interested in catalysis, the density is not going to be the same. Gas phase diffusion, you can expect that there will be density gradients, right? So you shouldn't be using DAB grad CA unless you have some other simplifications in mind. Okay, so this is only true for constant and binary. Now let's think of another example, another simplification, which is pseudo binary and constant rho. Pseudo binary and constant rho. And this is a simplification which actually is most commonly used, but it's not always clear or evident sometimes how to think about this. Is that now pseudo binary system visualize a liquid phase in mind and think there are several gases dissolved in it. Okay, so I also gave an example last time. Think water is there, water has dissolved nitrogen, water has dissolved carbon dioxide, water has dissolved oxygen. Now, we think that the species of carbon dioxide will interact a lot with other species or will it interact mostly with water? Mostly with water, right? Because the concentrations are going to be very small. It's really just dominated by water. So every species is sort of only interacting with water in a way. They can interact with each other. There's no doubt that they can react and so on. Obviously, there are liquid phase reactions. But in terms of sort of the maximum concentration it sees is actually of the water phase, right? So that's why when we say pseudo-binary, we generally imply that there are some things in a solvent. The solvent is the dominant concentration, and the concentration of that solvent is roughly constant. It is not exactly constant, it is roughly constant throughout, and we can write the flux as Ji minus Di grad Ci. And this is the most common formula you might have seen, where you don't even specify the diffusivity in what. It is implied that the diffusivity is in that solvent, right? I don't have a DAV, I just have a Di. The species I have the diffusion of carbon dioxide in water, diffusion of hydrogen in water, diffusion of oxygen in water, right? You don't specify the solvent, it is just diffusivity times gradient of Ci, okay? And basically, it is the same formula as the binary because it's pseudo binary. Just that you even drop the second phase because we know the second phase is always the solvent. Okay, go ahead.
So generally incompressible.
Absolutely. So if you can imagine that even for a binary system in a gas phase, you can have complication and you can obviously manage multi-component gas phase is the most complex because there you will have changing densities and so on. So yes, absolutely incompressible and some sort of like dissolved system. You should not have equal concentrations. Any questions? Great question. Any other questions here? All right, the final simplification you see is constant C. Now I'm saying I do not care about and binary and constant C. I don't care about constant rho. Now I'm thinking of a total concentration of A and B is the same. And I hope you can now guess it that we should now use the molar average velocity because the molar average velocity is based on concentration. So in this case, I will write JA of M is minus CDAB gradient of chi A, which is equal to minus CDAB gradient of CA by C. C gets cancelled much like this last time, and you simply get minus DAB grad CA. Okay. So you again get to the same answer, but right now it's constant, and this is the molar flux. This is the molar flux based on the molar average velocity. So I hope you can now see that they have two different JA and JAM have the same formula, but the velocities will be different. In one case, it's the mass average velocity. In another case, the molar average velocity. And we will do a problem in homework again to kind of drive home the point that you can use either definition, but one definition is just easier to use, but you can arrive at the same answer to other definition. So I would keep this sort of three cases handy. Whenever you have a problem, think about which case you have, and either use the mass average system or the molar average system. But at the end, you can see the definition of J reduces to DAB grad C. But the definition, but the molar average versus mass average distinction is important. Okay. Any questions at this point? I think that's you would like to get clarification on. All good. Okay, so I think this is a good time to have a break. Let's start at 12:50. So 12:50, we'll just return and start and have the second part of the lecture. Okay. We see in 5 minutes.
The summation of little ji 0 versus mass velocity. And the reverse is true that by big there is an example, just like in this scenario. Where, as you said, sometimes they are. Yes.
Oh, yeah, of course.
What is the example?
Yeah, so that is one of the to cover that. Where I show how small GIs are zero, capital GIs are not. And most of the common cases they will not use that because you have a very special sort of relationship to have both of them. One of them has to be zero.
It's a special relationship. That makes sense.
Zero. So one of them will always be zero. Then there is small GI or capital GI, depending on defining it. But for both of them to be zero, that's
So why is it that people have so you have that equation so this is but it's on big JI, not on certain cases. So that's so is that the biggest important relationship? You want to say
yeah, I mean, I think, yeah, I mean, your question, if I understand the question, I would say this is just one more clarification. One relationship to remember is that
when you choose the mass and velocity, you put mass and velocity to consider for zero. If you choose molar average velocity, you calculate yes. Other is a system that students will get small things. Other one just pick one. I think it's yeah. So most of the time without this, but you do a problem in class will be using this but then you will also force to do the other approach and this is just what we do. Get to the same answer. But this is what it is. Yeah, so yeah, I know what you're saying. Basically, the reason you write like this is because you write yeah. The volume is small. That's why just redefined. Oh, sorry, the density is
So you will be just like taking out from the bottom.
yeah, volume constant. Because you have to define it in volume. But in reality, it is the output.
All right, let's begin. Second part of the lecture today. All right, so let's summarize what we have discussed till now. We have said that heat conduction is Q bar K minus T, minus K grad T. Then we have species diffusion, where we have J of I minus di grad Ci, and this is not always true. This is only true for constant rho slash binary. But I'm just writing this to kind of show some similarity. And something we will not do right now, but it is momentum diffusion, which will come to the second part of the course. I just want to highlight here for completeness. Momentum diffusion. It will be slightly different. It will be shear stress is mu del V. It's not a dot product. It is actually a tensor. So the left hand side is a tensor. Is the shear stress tensor. And don't worry if you have not seen this before. We will cover why you need a tensor. And this is known as the outer product. But what I wanted to highlight here is the fact that the V here is the mass average velocity. This is the most common definition that you will see. This V is the same as the mass average velocity we're defining. And mu del V, where mu is the viscosity. And I will just tell you the units right now. Units of shear stress are kg per meter second square. And the units of viscosity are kg per meter second. Okay. This is just for completeness. And we'll discuss this in a lot more detail later. But you can see there are some similarities. They both have a gradient, but the difference being that there is no negative sign here, and we actually have a tensor relationship. Some books actually do use a negative sign, but I will say it's more common to not have a negative sign in shear stress. This is kind of the more conventional notation. You can have a negative sign if you're very, adamant. You can have it. You just have to change all the equations. So the question now is, these are the three main transport mechanisms we will discuss in this course: heat, mass, and momentum. Okay, heat, mass, and momentum. These are the three things we will discuss in the course. One thing that does come up, and this is still chapter 1 of these book, is how do we compare these three different transport processes? Okay? The challenge is that the units of viscosity are kg per meter second, diffusivities are meters square per second, and this is joule per meter second Kelvin. So how do we compare three different transports when the constants in front of the gradients are different units? And for that, it is very common to define an effective diffusivity. We already know the diffusivity for the units of meters square per second, but we will now define variables to bring sort of thermal conductivity and viscosity in the units of diffusivity. And that's called thermal diffusivity and momentum diffusivity. And I'll just define them now. So thermal diffusivity is K by rho Cp. The Cp is the heat capacity. And this is known as joule per mole, joule per kg Kelvin. Kg Kelvin. K, remember that K is joule per meter second Kelvin. And this is kg per meter cube. This alpha is known as the thermal diffusivity. Thermal diffusivity. And this also has the units of meter square per second. Okay. This is one way you can kind of start to compare now that we have defined this variable. And why have we come to rho Cp is because, and we'll discuss this in a little bit more detail in a few minutes, the rho Cp times temperature is sort of like an enthalpy. So kind of like an enthalpy per volume. And so that's why you kind of divide it by that to get diffusivity like this. Di is simply meter square per second, so we don't have to change it. But then we also define momentum diffusivity nu, sometimes known as kinematic viscosity. This is momentum diffusivity. Momentum diffusivity. And remember, this has units of kg per meter second. Kg per meter second. And this is kg per meter cube. So you get the units of back as meter square per second. Okay. So meter square per second, meter square per second, meter square per second. So now we have three transport processes that we have. We can compare by comparing the values of alpha, di, and now I have taught this course enough number of times to know that students hate dimensionless groups and they feel like this is confusing. But I want to emphasize something here which students many times forget is that know that these are material properties. These are not properties of the system. You can pick a species. You can say, well, I know the viscosity, I know the density, I know the heat capacity, I know the thermal conductivity, I know the density. So these are the things you already can tell, or you can have these are material properties. They don't refer, these are sort of like inherent to that sort of species or and so on. They don't, for instance, get modified because of the flow, right? So now what the dimensions which we will define are material properties to compare these different transport processes. Okay, they are not dependent on the flow property or the transport broadly. These are just to give you a sense of how different transport processes happen. So what I'm trying to say here is that if I want to compare, momentum, is known as the Prandtl number, and that is basically momentum by thermal, okay, and that is naturally mu by alpha. This is mu by rho by k by rho Cp, and that becomes mu Cp by k. So again, you can find this Prandtl number for typical liquids, gases, and so on. Right? Prandtl number helps you compare all these things. And if you read in the book actually derives this for gas. They actually show you how you can find this for an ideal gas, which is pretty cool. If you're interested, you can take a look. But Prandtl number essentially is 1 for gases. Prandtl number is about, I think, hundreds to thousands. 1 to 10 for liquids. And For polymers, and I know some of you will be working in polymers, it is even higher because the viscosity of polymers are high. If polymers have much higher viscosity, the mu goes up, so that's even higher for them. So what does this tell us? It tells us that momentum actually dominates, right? So momentum diffusion dominates over the thermal part. So if I'm trying to transfer momentum, it will go faster than trying to heat something. The thermal conduction will be slower than momentum diffusion. Similarly, there is something known as a Schmidt number. Schmidt number, and it is momentum by diffusion, and that is mu by dAV or mu by rho dAV or di, like doesn't matter. And Schmidt number is also one for gases, but Schmidt number is almost 100 to 1000 for liquids. And obviously it's even higher for polymers. So Schmidt number allows me to compare momentum to species diffusion. And in gases, so not gases, why are gases complex? Gases are more complex because all transport processes are equal. Prandtl number is 1. Schmidt number is 1. When you want to model a gas and you want to understand transport of gaseous phases, it's much more complex because everything is equal. So you cannot ignore anything. But when you see these big numbers, you can imagine that you can ignore what are the transport processes in stuff like polymers or liquids and so on. Okay. Does that make sense? So let's do another question just to kind of drive home the point here, and hopefully all of you can see this now. So with this in mind, let's have this question. In typical liquids, which transport is faster, species or heat conduction? So we haven't discussed this ratio yet, but hopefully you will be able to see this on your screen in a few seconds. And yes, I hope you can all see it. Let's wait for a 1 minute or so, and then please submit your responses. Which transport is faster in liquids? Is it species diffusion or heat conduction? So I'm still waiting for 7 or 8 students. Then another 15, 20 seconds. All right, 2 more responses. I think we are good. Let me just wait for 5 seconds in case. Yeah. Few more seconds. All right, let's end this now. Let's look at the results. So it's split. So it's 40%, 60% roughly. So I will now let you talk to your neighbor, convince each other what answers to pick, and try to convince each other and see how you got the answer.
Yeah, okay. Yeah, so that makes sense. Because we were just like, it's not. Yep.
All right, so let's take a look at the answer now. And I'm pretty sure some of you realize that you probably just had the ratio wrong or something like that. But the idea is the same, that we know the Schmidt number and the Prandtl number. Schmidt number is momentum by diffusion by momentum by thermal. So it becomes thermal by diffusion. And this LE is known as the Lewis number. Known as the Lewis number, which is simply the ratio of Schmidt to Prandtl. And because Schmidt is larger for liquids and Prandtl, the Lewis number is also greater than 1. So you get thermal by diffusion. So thermal is faster. The simple way to remember this, and I've always remembered this, is that heat in a liquid transports faster than species. Okay? So if I take a liquid and I am trying to dissolve a gas, the gas will sort of transport slower, the heat will transport faster. I will be able to heat a liquid faster just by purely diffusion. Okay? We're not thinking about convection or anything. Just if I have a stationary column of liquid, I have exposure to heat, the heat will transport faster. And let's say if I'm dissolving at the same time some species, it will go slower because heat transports faster than a liquid than species. Okay, so that's the I've never forgotten this line. Always remember this. That is one way to remember that diffusion is the species diffusion is the slowest process in a liquid. It's the slowest. It takes the longest. So I forget maybe which lab was it, but I had a student who came to me and was discussing this problem. I was like, well, you know that heat will transport faster than liquid, right? So that way you can understand, you can focus on thermal first, and then you can try to resolve the diffusion problem and so on. So just remember, this is a nice, simple, kind of line to remember. Any questions at this point? Yes, please. Correct. If you, I would say it doesn't matter more necessarily, but it is going to be more dominant than the other. But let's say, so let me give you an example of how this is interesting. So you have a problem where both temperature is changing and concentration is changing. So you know that concentration is changing very slowly, right? So you can first solve the temperature problem, say it has reached a steady state, but it's so fast, and then solve the concentration problem, because concentration is evolving much more. That is one way to think about it, that if it's 100 and 1000 times faster, then I can simply focus more on the temperature. Sorry, assume that the temperature has completely equilibrated or kind of developed fully, and then solve the concentration. That's one way you can use this model. So it doesn't necessarily mean it matters more, but it is dominant. It is faster. Any other questions? All right, so let's go further now. Last 10 minutes, we will do some constitutive equations. So the last part we will discuss today is constitutive equations. Constitutive equations. So you remember that I had said that the learning goal of this course is governing equations, boundary conditions, initial conditions. Okay. So till now we have been discussing what are different kinds of transport processes, how do we define fluxes, what are the relative rates, but we haven't really come to the main point, which is to be able to predict the concentration, temperature, and velocity. These are the things you want to predict. So how do we go about from fluxes to predicting these things? And that's where constitutive equations are governing equations come. So we'll focus on the fluid flow part in the second part of the course, but in this part, first part of the course, we'll focus more on the temperature and concentration. Okay. So what I will do is I will derive one equation and then generalize it to 3 different equations. So what we'll do is we'll write constitutive equations for a scalar B. Okay. We'll assume there is a scalar B which has flux F and which has volumetric generation BV. Okay, BV. This is per unit volume. So we'll discuss this in a little bit more detail. And the scalar can be a few things. So what can the scalar be? So so that we don't repeat derivations, we are doing this. Let's say we have a scalar B, flux, and a volumetric generation. So these are all scalars. Only the flux is a vector. So if my scalar is concentration, Ci, I know the flux, right? I know the molar flux. I will use mass average velocity. You can use molar average velocity as well. Let's use mass average velocity. Then we know the flux is Ci V minus di grad Ci. And what is an implicit assumption here? The implicit assumption is that this is only true for pseudo binary and constant rho. So don't forget that, okay? Pseudo binary constant rho, okay? That's why I'm writing it as minus di grad C. Otherwise, I won't be able to write the diffusive flux as minus di grad C. If you don't have pseudo binary, you will have to do all the omega A, grad phi, and so on. But this is only true for constant pseudo binary. Now, what do you think? How can like if we generate or consume any concentration? Reactions, right? You can have some reactions, and right now, remember, this is probably again students confuse. This is volumetric reaction. Okay, you can also have surface reactions. We are only talking about volumetric reactions right now. So this is Ri here. Okay, and just to drive home the point, Ri has the units of mole per meter cube per second. Mole per meter cube because it's volumetric reaction per unit volume. Mole per meter cube second. Similarly, you can also have this the scalar to be temperature. So let's say if it is temperature, it can also have some which we hadn't discussed till now. It can go by some sort of convective flux, rho CPTV. And this rho CPTV is actually rho CPTV enthalpy, which I was mentioning earlier. So we are just convecting this enthalpy, or it can diffuse using the heat conduction minus K grad T. Okay. So rho CPTV minus K grad T, and this is, and it can have some heat generation, joule per meter cube second. So what is an example of a heat generation? Recoil or reaction, or some electric heating or so on, that is joule per meter cube second. All right, and my favorite scalar here is the total density. Okay, total density rho. And now I'm looking to get an answer of what is going to be the total flux. And I want to, what do you think is the total flux? Total density rho. Okay, so I think we're going in the right direction. So slightly, yeah, you're in the right direction, thinking a little bit more. So note we have two different kinds of fluxes, right? One is convection and one is diffusion, right? So as was correctly pointed out, there should be convection, rho times V. What is the diffusion? What is the diffusive flux for total density? Zero, right? Because we discussed that if we have all the fluxes together, if we have all the components together, they cannot diffuse. We just cannot diffuse because the summation of small ji is zero. So if I use the mass average velocity here, rho v, then I will have a summation of ji here, but we know that is equal to 0. So it's only rho v. It cannot have diffusion, just convection. There is no diffusion, just convection, right? When thinking of the total density, this cannot have any diffusion. By definition, diffusion goes away, right? In others, you have diffusion because we are talking about temperature or an individual species. Okay, makes sense? Any confusion at this point? All right. So now let's do another question here at this point. Last question for the class. What is the generation term VV for total density? So what do you think would be the right hand column here for total density? I will start the poll now. All right, let's do this. Hopefully in a few seconds, you should be able to see it on your screens. Greater than 0, less than 0, equal to 0, or needs more information. Yeah, it's on now. Let's take a quick, maybe 45 seconds to log your answer. Few more responses still left. All right, I think everybody has recorded your answer. Oh, now we have a few more. All right, so let's stop here. I'll stop the question. and we'll look at the results. So most of you say 0. Some of you have different answers. So maybe we can have a quick volunteer of why it is 0. You chose 0. Anybody? When it is selected 0, but why? Anybody? Just no. Any thought?
Why don't you change the following?
I think you're going to the right, you're going to the right point. Anybody else?
Extensively.
Yeah, because total density represents the mass. Mass can neither be generated nor consumed, right? Most can be generated and consumed, but not mass, right? So you cannot have a volumetric generation of mass. It has to be 0.
So you basically simply get here, you get simply here 0 because mass cannot be generated / consumed. All right, we will not discuss another example here, but I would encourage you to think about C here. If I have a scalar C, right, small c here, you would get C times V of M. You will choose a molar average velocity. Then your flux will go away, but then think about whether you will get a volumetric generation term or not. I would encourage you to think about that. If not, then we can chat about it in the next lecture. Okay, but hopefully let's focus on these three scalars. Hopefully these make sense. Mass can either be created or consumed, and we have rho times V, which is the only conductor. So now, with that information, how would we write conservation equation? So let's consider a control volume, which hopefully some of you have seen before. If not, let's do it now. We have an X, Y, Z. We'll take a control volume like this. I'm going a little fast because there is a full video we have on this derivation. So I'm going a bit faster here, but let's do this. Delta Y, delta Z. And we want to understand how the conservation equation will work here of a scalar B, okay? And we'll use in minus out plus generated equal to accumulated. This sort of a term saying that a scalar, in case of concentration, it's a species balance. In case of temperature, it is the energy balance. And in case of total density, it's the mass balance, right? Mass in minus mass out plus mass generated equals mass accumulated, so on, concentration in, flux in, flux out. So this is basically the definition. When we are thinking of in and out, we are thinking of surfaces, right? They cannot come and they have to come to one of the surfaces. So, and if I have the x direction, this is known as f of x. And this is known as f of x plus delta x. Okay, so I will shade these to make sure it's clear. These two surfaces on the YZ plane, fx and fx plus delta x. So which of the flux is in here? Fx, right? And fx is the one which is out, away from the surface. So, and why am I choosing fx? Because my surface is perpendicular to x, right? So if I am not thinking of, let's change the color to make sure it's clear. If I'm thinking of fy, if I'm thinking of fy, then I will look here, right? fy plus delta y, right? And these are let's try to maybe be consistent. This is this surface, right? fy plus delta y. Similarly, you will have fz, fz in this direction, fz plus delta z. Okay, so we'll have something like this. These are the ins and out, and ins and out are, I'm choosing x, y, and z like the subscript because I only care about the flux in the x direction when I'm looking at the surfaces perpendicular to x. I'm only looking at the fluxes in the y direction when I'm looking at fluxes perpendicular to the y direction. All right, so with that in mind, we'll say basically fx, this is flux per unit area. So we'll have delta y, delta z, that is in, minus fx plus delta x, delta y, delta z. This is in. Maybe let me just make sure I'm using the same color. hopefully make it a little bit clearer. So fx delta y delta z minus fx delta y delta z x plus delta x delta y delta z. Then I have, and I'll stop here because I know we are running out of time, plus fy delta x delta z minus fy plus delta y delta x delta z plus fz delta x delta y minus fz z delta x delta y. Okay, so this is the in minus out plus generated. We have already discussed it. It is plus BV volumetric generation delta x delta y delta z is equal to del B by del T times delta x delta y delta z. Okay, so I'll stop here. We'll discuss and try to simplify this equation in the next lecture. But essentially, this is in minus out through surfaces plus a generated term, and then the accumulated, which is time derivative. And we'll talk a little bit more about this. Okay. So I don't want to go over time, but I hope you can see how we are coming together to find conservation equation. And then we'll substitute the values of f, b, and bv to get three different equations from one derivation. Okay, so we'll do that in the next lecture. So I look forward to seeing you on Monday. I have office hours, so if you want to have any questions, I'll be here, and you can go over to my office if you have any questions. All right, I look forward to seeing you all on Monday. And Felipe has office hours on Friday, and if you have any questions, he will be available as well. All right, thank you.